The last section that we need to cover for the test is improper integrals. Okay, so named because there's something rather improper about them. So if I have 1 to infinity 1 over x cubed dx, integrating this is actually a relatively easy affair, right? If I have, 1 over x cubed dx, that's x to the negative 3 dx, or that winds up being x to the negative 2 over negative 2, or negative 1 over 2x squared, right? But here's the thing. If I actually integrate it that way and try to plug in the limits of integration, it doesn't really mean anything to plug infinity in. From our vantage point, infinity is not a proper number to use as a limit of integration. So what I need to do is I need to actually figure out a way around that. So instead of dealing with the mathematics of equality, we are going to make recourse again to the mathematics of approach. And instead of going from 1 to infinity, I'm going to go from 1 to b, and then I'm going to take that integral and plop it inside of a limit and evaluate the limit as b goes to infinity. Okay? So I'm sort of cheating. I'm basically getting around the idea that I can't use infinity when I'm dealing with mathematics of equality, and instead I'm using mathematics of approach to sort of get around that problem. Okay? So if I go ahead and evaluate that, and I've already done the integration over here from 1 to b, I recognize the fact that I'm going to get negative 1 over 2b squared minus a negative 1 over 2. Okay? And of course those negatives will cancel out. Well, what happens to this term as b approaches infinity? This goes to 0, and therefore the limit goes to 1/2. So we actually do have an area that has sort of an infinite interval, but a finite area. But what you're going to find out is that not all of these actually wind up going to a specific number. Some of them actually don't, okay? So let's go ahead and let's take a look at, I don't know. Let's go same interval, and let's do it for root x, okay? So if I have the limit as b goes to infinity of 1 to b of x to the negative 1/2 dx, I recognize the fact that my integration should be relatively straightforward. I'm going to get 2x to the 1/2 from 1 to b, okay? And therefore I'm going to get the limit as b goes to infinity of 2 root b minus 2 root 1. When I plug in infinity for that, this goes to infinity. This does not converge to a known finite number. It actually is what is called divergent. Well, we've undone the power rule and we've dealt with integrals often enough to know that root x, because that is within a hair's breadth of 0, when I integrate, I'm going to get a positive exponent. Okay? I'm going to get a positive exponent, and therefore when I plug infinity in, trying to evaluate the limit, I'm going to get an infinite number. The reason why this worked right here is that even after I integrated, I still had a negative exponent because it wasn't within 1 unit of 0, and therefore I can basically make sort of this rule by hunch that if I'm within 1 unit, if my power right here is within 1 unit of 0, it's going to be divergent. If it's not within 1, if it's more negative than negative 1, I'm going to get a convergent value, and I'm actually going to get an actual value. Okay, well, that means that if I have the integral as a goes to infinity of 1 over x, and we'll just call it p dx, I know that when p is greater than 1 and when p is less than 1, those have two different outcomes. If p is greater than 1, it's convergent. If p is less than 1, it's going to be divergent. Okay? Divergent, convergent. Okay? Or, and so basically the only thing that I haven't figured out is what happens when it's actually equal to 1. Well, when it's actually equal to 1, and let's go 1 to infinity of 1 over x dx, I recognize that it's going to wind up being a natural log function. Okay? And so from 1 to b of 1 over x dx winds up being the limit as b approaches infinity of natural log x from 1 to b, or the limit as b approaches infinity of natural log b minus natural log 1. Now this goes to 0, or it actually is 0, right? This, however, goes to infinity. As much as the natural log function does not increase aggressively, it still is an increasing function on the whole of its domain. So basically, I need to go ahead and include the equals 1 on the divergent. Okay? So basically, you can figure out if it's just in this form, if p is greater than 1, even if it's like 1.000001, it's going to be convergent. If it's equal to or less than 1, meaning still negative, but less than 1, so 0.76 or something like that, it's going to be divergent. Okay? Now those are the easy ones, and that's actually a theorem in your book on page 523, and you can look that up at your leisure. What becomes a little more hairy is when you start dealing with ones that are something like this. Now, what does our hunch tell us is going to happen on that particular problem? Well, I know that once I start integrating, I'm going to have to use parts. That's easy enough to figure out. But I know that once I deal with this limit as b goes to infinity of 0 to b, I recognize that really this is this. Is that denominator strong enough to drive the function toward the x-axis fast enough such that this infinite interval still yields a finite area? And my hunch on this one is yes, because the denominator is an exponential, and exponentials are so much more aggressive than anything that's polynomial. So let's go ahead, and I'm just going to I don't want to deal with the parts in the midst of all of this, so I'm going to kind of do something that I usually don't do. I'm going to go ahead and pull this over here, and we are going to we're going to go ahead and do parts over here. dv is equal to e to the negative x over 4 dx, and v is equal to negative 4 e to the negative x over 4. So what happens here is this winds up being negative 4x e to the negative x over 4 minus, or actually plus, since it's going to, this minus is going to cancel it out, e to the negative x over 4 dx, or negative 4x e to the negative x over 4 minus 16 e to the negative x over 4. And you can go ahead and pull out a negative 4 if you want, and that's x plus 4 over e to the x over 4. Whew. Okay, well that was, frustrating enough. But let's go ahead and plug it in and see what that gives me, okay? Let's sort of leave that off to the side. So I have the limit as b goes to infinity of negative 4 x plus 4 e to the x over 4 from 0 to b. Well, that means I have the limit as b approaches infinity, and we'll go ahead and put brackets, negative 4 b plus 4 e to the b over 4 plus, minus a negative, 0 plus 4e to the 0, and there you go. Well, this is obviously going to be a finite number, right? This is 16. And if you're curious about this one, you see the fact that this is going to be exponential down in the denominator. This is going to be linear. Well, it's infinity over infinity, right? Well, that's an indeterminate form, so I can go ahead and use L'Hopital's, and L'Hopital's one round is going to make that numerator disappear, and so this actually winds up going to 0, okay? And I actually get a finite area, and unless I made an arithmetic mistake, it's 16, okay? Now that should be straightforward enough. The whole idea is that you're not allowed to sort of plug these numbers in. The limits of integration are improper. So you're just applying a limit to these infinitely wide intervals such that it sort of makes it legal, okay? Well, let's go ahead and do x squared e to the negative x dx and see what happens there. Well, instead of a linear over an exponential, this is going to be a polynomial over an exponential. It's still going to be parts, but since it's x squared, let's go ahead and use the tabular method. Okay. I know plus, minus, I know that's going to be x squared, 2x, 2, and 0. E to the negative x, negative e to the negative x, e to the negative x, negative e to the negative x. And remember that when I do tabular method, it goes over and down, over and down, over and down. So that's 3 pieces right there. Oh, I forgot to give you the limits of integration. Sorry, it's going to be 0 to infinity. Okay, well, let's do the limit as b goes to infinity. And I'm using b just because when we don't know what a limit is, or when we don't know what the interval is, or when we want to talk about intervals in general, we usually go a to b. And if I were plugging in for this one, I'd be plugging in a approaches whatever, okay? Of x squared e to the negative x dx winds up being the limit as b goes to infinity. And I'm going to go ahead and clean this up a little bit because you can factor out a negative e to the negative x out of a lot of this, because basically this winds up being negative x squared e to the negative x, negative 2x e to the negative x, minus 2 e to the negative x. You can factor out a negative e to the negative x, and you're going to get x squared plus 2x plus 2. So let's do x squared plus 2x plus 2 over negative e to the x from 0 to b. That means that I have the limit as b approaches infinity of b squared plus 2b plus 2 over negative e to the b minus, and of course when you plug in 0, you're going to get 2 over negative 1. Boom, boom. This, of course, is 2. The question is what happens here. Again, you can do L'Hopital's rule and recognize the fact that the numerator, after a couple rounds, is going to disappear. And so this goes to 0. This area is 2. That winds up being, kind of neat. Okay. Let's go ahead and do, let's do 1 or 2 more. See if we can sort of squeeze in a few more before we get going on the next subtopic in this. So let's say I'm going from 0 to infinity, 1 over e to the x plus e to the negative x dx. Well, I know that I can change the form of that. Changing the form of that really isn't that big of a deal, as long as you see it. I don't really like that e to the negative x. So what do you say I multiply that rational expression in the integrand by e to the x over e to the x? And I wind up with e to the x over e to the 2x plus 1. Well, that is a whole lot better because that's arctan. And if I go ahead and do the limit as b approaches infinity of 0 to b of e to the x, and I'll go ahead and make it a little more explicit that it's arctan, I get that. So the limit as b approaches infinity of arctan e to the x from 0 to b winds up being the limit as b approaches infinity of arctan e to the b minus arctan e to the 0. Well, arctan e to the b is going to be arctan e to the infinity. As b approaches infinity, e of b approaches infinity, and arctan approaches what? It approaches its asymptote at pi over 2. So this is pi over 2, and of course this right here is what? Arctan of 1. Well, arctan of 1 is pi over 4, so your area is pi over 4, convergent. All right. Well, let's go ahead and do this one. Let's go 1 to infinity. We have natural log x over x dx. Okay. Actually, let's hold on to this one. Okay, let's do another one with the exponentials. E to the x over 1 plus e to the x dx. Okay. Well, here's the thing. That is natural log. So if I want to do the limit as b approaches infinity of 0 to b of e to the x 1 plus e to the x dx, I recognize the fact that that is b approaches infinity of natural log 1 plus e to the x. I don't really need the absolute value bars because it's never going to be negative, but whatever. And I have the limit as b approaches infinity of the limit of natural log, 1 plus e to the b minus natural log 1 plus e to the 0. Okay? Well, this right here is just natural log 2. The question is, what happens here? Well, natural log is an increasing function. Okay? So this, as slow as it actually gets there, actually goes to infinity. So this does not have a finite area. It is divergent. Okay, last one for this particular video. Let's get back to the one that I started to do last time. We have natural log x over x dx. And that means I have the limit as b approaches infinity of 1 to the b natural log x 1 over x dx. That winds up putting it into a very easy u sub sort of situation. So I have the limit as b approaches infinity of 1/2 natural log x, the whole thing squared. So that's the function squared, not the argument. And so I have the limit as b approaches infinity of 1/2 natural log b quantity squared minus 1/2 natural log 1 quantity squared. Well, that right there is 0, because natural log 1 is 0. And of course, as b approaches infinity, natural log b is going to approach infinity. So natural log b squared times 1/2 is going to approach infinity. This, again, is divergent. But could I have done this one another way? Well, I already know that 1 over x dx is going to be divergent. Okay? Well, here's the thing. I can actually come to the conclusion that it's divergent by comparing them. Because for all x greater than e, meaning that once I get beyond e, from e to infinity, the natural log x over x is greater than 1 over x. And what happens between 1 and e, which remember is about 2.78, 2.7 something. All right, between 1 and e, the fact that 1 over x is higher is negligible because that's such a small portion of the interval. But since for the rest of the interval from e, basically from e to infinity, this is true. Well, if this is divergent and this is larger than a divergent function, then it has to be divergent, okay, by what's called the comparison test. Right? And we'll talk more about that in the next video, but I at least wanted to introduce it right here. Now, what has been common to all of these is the fact that I had an infinite interval. There are other types of improper integrals which bump up next to asymptotes, which is just an infinite interval along the range instead of an infinite interval along the domain, and it's that will be the topic of the next video.